Now, when we train the model and then score and then evaluate, we can see these metrics come out. Then we need to figure out what these values mean. We will also look at whether this value is good if it is high, or if it is low it is good. Let's imagine if we had this kind of data. These red dots on the x and y axes are data point existed. But when I train a machine learning model that satisfies this data, let's say we were able to create a line like this. In that case, this line will have some specific function value. When this function is found, we have the value of the original data and then the value predicted by the function created by the function. By comparing the difference between the two, we judge how well this model is made. Then everyone think about it. Is it good if the difference between the original data value and the predicted value by the model is large or small? The lower the difference between the values, the closer the model fits to the actual value. So, the smaller the difference between the value of the original data and the value predicted by the model, the better. Then you can express the difference like this. But if you try to lower this value, if it becomes negative, you will have a problem. If it becomes negative, it will keep going down to the negative number. So that it doesn't become negative, we put an absolute value. This is the absolute error. Absolute value. Then, this absolute error is not compared for only one data, but for all data. The total average error can be obtained by summing the error and dividing it by the total number. That is the mean absolute error. And we don't use this absolute, but there is also a way to square it and then root it. Even if you do this, you won't get a negative number. This is the root mean squared error. So, the metric values you saw on the screen are the ones that calculated the error in this way. The lower these error values are, the better the model is. We will move back to the result value. The result came out like this. The mean absolute error value was about 8,100. And the root mean squared error was about 13,000. You can see that the error value is quite large. The average of the weekly sales we have is about 15,000. But because about half the average value is the error value, the error value is quite large. You can see that the model is not so well made. So, for these error values, the lower the value, the better. Then the coefficient of determination is usually said to be R². Probably, those who have worked with data and charts in Excel have seen a lot of R² values. This value means how similar the created model and data are. The closer this value is to 1, the closer it is, the higher it is, the better the model. But I don't think that 0.6 is not a very high value. So it seems that the model we made is not a very good model. Let's make another model. Now, we will come out with a boosted decision tree algorithm in the initialize model and regression. Then, right-click and copy the train model we used. And then right-click and paste in an empty place to use the same train model. Please connect this algorithm and train model like this. We want to compare the algorithmic changes when training a model with the same data. Then the data should be used the same. Please connect split data. Then we also need the score model. Copy and paste the score model as well. For the score model that came out like that, this is the trained model and the rest of the circles are connected with 20% of the split data. Then, if you connect the score model with the evaluate model again, you can create two models at once and compare the models. The screen looks a little complicated. It may seem like a lot of complexity because it's just connected. But it's exactly the same flow we on the left before, but just think that the kind of algorithm has changed. In this state, I will right-click the Evaluate model and run selected. Then the new model will be trained on evaluated. The second algorithm we train is a slightly more complex type of algorithm than the first linear regression. It will take a little longer because it is a method of finding a rule while stretching out several branches using an algorithm called a binary classification decision tree. When this is done, a green mark will appear. And then click on the lower circle here to visualize. Now, you can see two metrics appear on the screen here. The metric in the left here is the result of the first linear regression. Then here is the result of the newly trained boosted decision algorithm by the metric in the right. Let's compare. I explained earlier that the lower the error value is and the closer the coefficient of determination is to 1, the better the model and the well-trained model. As you can see, the error value of the first model was 8,000. But the error was reduced by half in the second newly created model, about 4,100. Then the root mean squared error was 13,000, which was reduced to about 7,000. Not only that, but the coefficient of determination was originally about 0.65. You can see that it has improved to 0.9. How is it? I trained and evaluated with the same data, but you can see that the results of the model are very different depending on which algorithm is selected. In this case, the data we have is a bit complicated. So, you can see through comparison that a slightly more complex boosted decision regression algorithm is more suitable than a simple model, linear regression. Now, this is how we like this model. You can use this model. And if you want to improve this model a little more, you can adjust various parameter values of the algorithm in the Properties window when you select this algorithm. So, each algorithm has a different parameter value. In our case, we found that the boosted decision tree is more suitable than the linear regression. Another way is to use the same algorithm but adjust the parameter values in it to create a new model. So, how many trees are we going to make? And how much will the learning speed be? Depending on this, the complexity of the model and the learning speed will be different. So, it would be nice to make a better model by changing these values a little more. In our lecture, model training will be finished here. Have you tried improving the model a little more? We only made 2 models. I think it would be nice if you could make it more diverse. Then, it would be a pity to end with simply training the model made like this. How to use this by choosing a good model from the mid models. Azure ML Studio provides it, so let's take a closer look at that part. If you train more, there may be different kinds of models. Among them, you can leave only good models and delete models like linear regression that did not perform well by right-clicking. Delete this. And also delete the evaluate model. Then only the algorithms, train models, and score models that were good among what we learn like this will remain. Leave the top as it is. When we work hard to train a model, we make several models and evaluate them. But after learning the models, we only need to leave one of the best ones if we decide, yes, this is the best model, IY. It's okay to erase everything else. I only left this one by boosted decision regression. In order to use this trained model in web or app, it is necessary to distribute this model to the web. That we call web deploy. In general, we have to have a lot of different conditions for just training and deploying models in a Jupyter notebook. However, Azure ML Studio builds the basic environment, so you can use the model very easily.